Hey, and welcome back. So here we are talking about part 2 of section 4.3, and we're going to talk about concavity. You guys have introduced to concavity in pre-calculus and maybe even algebra 2 if you have some graph, and we're taking a look at it. Alright, we're said a graph is considered concave down in this section right here, okay, because it is, concave down like a frown, and over here it switches over to concave up like a cup. Okay, so the way concavity is actually described mathematically is to say that a function is concave up on the open interval, some open interval, this is key, open interval, okay, if y prime is increasing. And it's concave down if y prime is decreasing on another open interval. So what does it mean for y prime to be increasing? Well, if y prime is increasing, that means that y double prime is greater than 0. And what does it mean for y prime to be decreasing? That means y double prime is less than 0. Oh. Okay, so let's see how this can be used in a couple of different examples. So our first example here is going to be for y equals x squared, and we're going to look at this interval for between 3 and 10. I'm going to just get rid of b because we have another slide for that. So I start taking a look, and so use the concavity test to determine the concavity of the given functions on these intervals. So my concavity test means I need to go and find the second derivative. So y prime for this one is equal to 2x, and y double prime is equal to 2. Well, when I take a look at the interval between 3 and 10, look, there's no x value here, right? So in y double prime, so what does y double prime look like? Y double prime, okay, looks like this, right? Here's 2. And again, the interval I'm looking at here is between 3 and 10, that open interval there. And look, y double prime is always greater than 0. So what does it tell me on between 3 and 10? Okay, well, between 3 and 10, actually everywhere on x squared, am I concave up? Okay, you would say since y double prime is greater than 0 on the interval 3 to 10, y is concave up. On the same interval. Okay, you gotta remember to write your sentences. You're showing stuff. You're justifying why you're saying your statements. Well, that can go in. Let's take a look at the second one. The second one looks a little bit more complicated. Okay, the second one looks like this. Okay, so y prime. Let's find y prime. Derivative of 3 is 0. Derivative of sine is cosine of x. Y double prime is equal to negative sine of x. And I'm looking at the interval between 0 and 2 pi. And it's the open interval. So what do I need to know? I need to know what is y double prime 0. Because if it's 0, I'll be able to tell between when is it positive and when is it negative, because I know it switches someplace when it's equal to 0. So if I find out when y double prime is 0, well, y double prime is 0 when sine of x is 0, or when sine of x is 0. Well, sine of x is 0, okay, at 0 and at pi. But notice we're only worried about the open interval, right? So I'm going to go ahead and say y double prime. And again, just for kicks and giggles, I'm at 0, at pi, and at 2 pi. All these places is where sine of x is 0. Okay, so what's happening between 0 and pi? Well, sine of x is normally positive, but y double prime is negative because it's negative sign, so it's negative here. What does that mean for y? Well, according to our concavity test, this is where it's concave down. And what about when y double prime is between pi and 2 pi? Well, y double prime between there, well, sine of x is normally negative, but negative means that y double prime is positive. And when y double prime is positive, that means that y is concave up. And then your sentence would look like, since y double prime is less than 0 on 0 to pi, y is concave up. Concave down on 0 to pi. Then you need to write a second sentence saying since y double prime is greater than 0 on the interval 0 pi to 2 pi, y is concave down, concave up on pi to 2 pi. So what does this look like graphically? Algebraically wise, I got this all taken care of. Well, what about graphically? Well, here's the graph. And more specifically, this is the graph of y, and this is the graph of y double prime. Notice right here is where pi is at. That's where I found it to be 0. And notice I said between 0 and pi, y double prime was negative. And so when I come up here, look right here, it's concave down from that section. And when y double prime was positive, y was concave up. I think that's kind of cool. I'm going to let that soak in. You got to let it marinate for a little bit. Look at everything that's happening in the relationship between y double prime and y. Okay? Pause the video if you need to. I'm moving on. So, what happens at the point, now we're going to talk about what happens at the point when concavity changes. You know, the place back here, okay, back here where concavity changes, this point right here where it changes is what we're going to call an inflection point. Okay? An inflection point is a couple of things that you need to know of. It's a point on the graph where a function has a tangent line and where the concavity changes. Okay? What does it mean to have a tangent line? It means that at that point it's differentiable. Differentiable. That's the key point. Okay? So a point in the graph where a function is differentiable and where the concavity changes. Okay? So that's what it means. Now here's the word of caution. A lot of people get super excited because a lot of people just say, well, you know, if I sit down here and I have a function, I don't know, y is equal to x to the 4th. And they get super excited. They go here and they say, well, y prime, well, that's just 4x cubed. Y double prime is equal to 12x squared. Well, at that point, then they would say, well, okay, so y double prime is equal to 0 when x is equal to 0. And then they would say there's an inflection point at x equals 0. And they wouldn't test it. It is imperative that you test this. Why? Because take a look. Right here is the graph of y equals x to the 4th. Notice here where we thought our concavity changed. It was right here, but it doesn't. And it's imperative that you do the test. It's imperative that you come here and you say, well, I think there might be an inflection point right here. Let's test it. So when I put in a negative number in for x into y double prime, well, negative times the negatives is positive. So, it's going to be a positive value, which means I'm concave up. Okay. Then when I do a positive number, I get the same thing. I get positive over here, so I'm also concave up. So I satisfied the first part of the definition of an inflection point. It is differentiable, okay? Because it's obviously I can, at this point it's very differentiable. I can take a derivative, okay? But the problem is that it does not change concavity, and you need to be cautious of that. Just because y double prime equals 0 does not mean I have an inflection point. You have to do the test for it, okay? Next. So when I'm sitting down here and I'm finding, okay, points of inflection. So I want to find all points of inflection on the graph, okay? So y is equal to e to the negative x squared. So let's do that. Again, what I need to do is just go find y prime. Here's my chain rule. Derivative of e to the something is really just e to the something again, times derivative of that something, which will be negative 2x. And I can rewrite that as negative 2x e to the negative x squared. Y double prime gets a little messier in that it's a product rule. I take leave the first one alone, and I multiply it by the derivative of the second. Well, the derivative of the second we already figured out as being e to the negative x squared times negative 2x. And then I do plus, take the derivative of the first, which would be negative 2, e to the negative x squared. And this gets complicated. And now I take a look at it, like, what can I take out of everything? Well, I can take out of everything a negative 2x, excuse me, not the x, negative 2 e to the negative x squared out of everything. And what I end up with is a negative 2x squared, excuse me, plus a 1. And again, I want to find out where it's 0. Well, what you should know is that this part will never be 0. And I set 0 is equal to a negative 2x squared plus a 1. And I solve for that, and I find out that, let's see here, 1/2 is equal to x squared. X is equal to plus or minus the square root of 1/2. Alright, so that tells me where y double prime is 0. But I still need to do the test to make sure that concavity switches. So again, here's y double prime. Okay. And I come over here and I find out, okay, so here I am at the square root, negative square root of 1/2. The positive square root of 1/2. And I gotta take a look. What happens? Well, when I choose a negative 1,000, well, a negative 1,000, well, out here that number is going to be negative. Out here, again, that number is going to be negative. So a negative times a negative is positive. This one here, I'll choose a 0. When I choose a 0 over here, okay, e to the 0 is just 1, so I have a negative out here. And then when I come over here and put 0 in, I have a positive. So a negative times a positive, negative. And then finally when I put a big positive 1,000, I get a negative number out here. I get another negative number in here. Negative times a negative is positive. So what I end up with is I have here what's happening with y. Here I have concave up, concave down, and finally concave up. So now I'm able to say that I do have inflection points, and my inflection points are located at plus or minus the square root of 1/2. You would say since y changes concavity at x equals plus or minus square root of 1/2, there are inflection inflection points at x is equal to plus or minus square root of 1/2. Okay, and there's your solution. All right, well, I think I'm going to, let's see here. Yeah, I'm going to go ahead and end it here. And this will be the end of part 2. And we'll do with part 3 in a little bit. See you for now. Talk to you later.